Okay. Thank you very much, Mr. Chairman. I am going to talk about the effect of heat treatments on the constituent materials of a nuclear reactor pressure vessel in hybrid environment. This is the beautiful logo of my university, the University of Salamanca. In 2 years we are going to celebrate the 800th anniversary. This is the oldest university in Spain, one of the 4 oldest in Europe, Bologna in Italy, Oxford in UK, and Paris in France being the other 3. Beautiful logo with the castle and the lion, the symbol of the Castilla and Leon region, the basis of the modern Spain. Hispania, a province of the Roman Empire. This is the bishop and the priest because it was founded by the Catholic Church. My co-authors are Diego Vergara and Miguel Lorenzo. We belong to the Fracture and Structural Integrity Research Group of the University of Salamanca. This old-fashioned. In 2 years we meet in Salamanca to celebrate this. We are going to organize several conferences. I am going to divide my presentation into 5 parts: introduction, stress-strain state, the important role of mechanical issues, the stress and strains on any environmentally assisted cracking process, hydrogen embrittlement, mechanical approach number 2, chemical approach number 3, discussion and conclusions. Let's go to the introduction. We deal with a nuclear reactor pressure vessel with 2 materials, a base material, shown B, low carbon steel, and a cladding material, stainless steel 316L, shown E, A, smaller width and bigger width. The wall is composed by a B material susceptible to hydrogen embrittlement. We here, in the red color, we have the inside part, hydrogenated environment, 300 degrees, and conventional environment, conventional air, 25 degrees. The objective is to evaluate the influence of the global stress-strain state, residual, influenced by tempering, heat treatment, plus thermal on the hydrogen embrittlement process. Let's go to the stress-strain state. What about the residual stress-strain state? We have residual stresses due to mechanical conditions, mechanical residual stresses, generated during the conforming process of the vessel, and they depend on the tempering process applied to the materials that constitute the wear. Residual stresses due to thermal conditions generated due to the existence of a gradient of temperature, inner and outer of the vessel. Here we have the equation to calculate the total residual stresses by adding the mechanical residual stresses but the thermal residual stresses. Here we have, from a reference by Kostilov and Margori, I think Russian guys, distribution of the residual stress-strain state due to mechanical conditions through the vessel wall. Here we have tensile area near the aggressive environment. Here this is the cladding, this is the low carbon based material, this is the 316L steel. We have higher tensile stresses near the aggressive environment, unfortunately, and regarding equilibrium we have compresses in the base material. And here we have the profile of strains, high tensile strains in the near aggressive environment area. Here we have the influence of tempering. The tempering time reduces the mechanical residual stresses in the vessel. You see the curve here. The higher the tempering time, the lower the stresses. And also the tempering temperature from 650 degrees to 670. Also the increase on tempering temperature reduces the mechanical residual stresses in the vessel. Here we have a more or less complicated plot, but we don't have time to get inside of the strength. Let's go to the residual stress-strain state. We have thermal-induced residual stresses. We assume 2 concentric tubes perfectly fitted with a relative sliding movement, the compatibility of strains, and we have thermal-induced residual stresses by strain compatibility. This is a thermoelastic program, and the total are the addition of mechanical plus thermally generated residual stresses. This is the global stress-strain state, and here we have the problem of the near aggressive environment area. This is the residual hydrostatic stress versus the width for different tempering times or for one tempering temperature. The higher the tempering time, the higher the residual stresses here, the tensile residual stresses. And here we have only the stress state suffers a remarkable change due to thermal gradient, while the strain remains almost unaffected. Let's go to the hydrogen embrittlement problem. Here we have the diffusion assisted by a stress and a strain field. Here we have the conventional diffusion, the thick term, regarding the negative gradient of concentration. The second term, diffusion, is assisted by the positive gradient of hydrostatic stress, and in addition, diffusion is assisted by the positive gradient of solubility, which is itself a function of the residual strain field, the plastic strain field. Then we have the gradient of concentration, the gradient of hydrostatic stress, and the gradient of solubility dependent of cumulative plastic strain. Using this equation, here we have the profiles of concentration normalized with regard to the concentration for the material free of stress and strain versus the depth in this B-material wall. This is the aggressive environment, and this is in depth. For different years of service, 1 year, 5 years, and 50 years. And for different tempering times, 1 hour and 100 hours. And this tempering temperature. Then, the lower the tempering time, the worse behavior against hydrogen embrittlement. Here we see that the black dots are always lower for higher tempering times. We have lower hydrogen concentration for different duration, for different service years. And this behavior is getting worse with years, because for 1 year we have a small difference between the two tempering times. For 5 years this is an appreciable difference, and for 50 years of operational level we have a clear difference of concentration levels for the two tempering times. With regard to the tempering temperature, 650 and 670, we have a really slight effect. In this case, we have worse behavior against hydrogen embrittlement for lower tempering temperature, but it is not easy to see. Here we have this behavior is getting worse with years. Again, almost no effect for 1 year of service time, a negligible effect for 5 years, and a more or less appreciable effect. This is better, the black color than the white color, lower concentration for higher tempering temperature. Tempering temperature affects less hydrogen embrittlement than tempering time, as we saw in the previous slide. Let's go to the discussion. This is the plot of the equilibrium approach, the quasi-static, quasi-stationary solution of the hydrogen diffusion problem. This is the concentration versus the concentration, the reference concentration for the material free of stress for a tempering temperature of 650 degrees, and this is the service time in years. As the time goes, we approach the asymptotic behavior, the equilibrium concentration of hydrogen. And we have the difference between the tempering time, 1 hour, 10 hours, and 100 hours. The best behavior, the lowest asymptotic equilibrium hydrogen concentration, is for the longest tempering time. Then, higher hydrogen with service time up to an equilibrium state, horizontal asymptote, green area, typical hydrogen diffusion trend. Hydrogen tends to a limit value with tempering temperature, horizontal asymptote, and with regard to the tempering temperature and tempering time, we have a plot of equilibrium concentration normalized with that for the material free of stress and strain for real functioning time of 1 to 2 years, and we have an increase of tempering time, red color, produces lower concentration, better hydrogen embrittlement behavior, and an increased green color of tempering temperature to 670 degrees produces also, in this case, a smaller decrease of concentration. Then the best thing to do is increasing in the heat treatment the tempering time, and if you can, this is less important, increasing the tempering temperature, because both actions produce a decrease in hydrogen concentration in the vessel. let's go to the conclusions. Stresses originated in the nuclear reactor pressure vessel wall are B-material with an interface. They are created by the gradient of temperature between inner and outer points, compatibility of strengths in the vessel. They increase the global stress level of the whole wall, thereby enhancing the development of hydrogen embrittlement process. The variables of the tempering heat treatment, tempering temperature, T-temp, and tempering time, again T-temp, minor letter, applied to the materials formed in the fission nuclear vessel wall, play a key role in the hydrogen embrittlement process. An increase of both tempering time and tempering temperature, the first one is more important than the second one, produces a decrease of hydrostatic tensile residual stresses at the B plus area with tensile residual stress area, the most dangerous area in contact with the abrasive solution. And this produces a decrease of hydrogen concentration and a decrease of hydrogen embrittlement. Both the increase of tempering temperature and tempering time. More important the time than the temperature. And that's all, I think, a final meta-conclusion, a conclusion after the conclusion. To guarantee the structural integrity of the nuclear reactor pressure vessel wall against hydrogen embrittlement, the tempering heat treatments applied to the constituent materials should reach the highest temperature allowed by such a treatment, and especially should have the longest possible duration. And that's all. Thank you very much for your kind attention.